Welcome students to the 8th lecture of fuzzy sets, arithmetic and logic. In the last class, I have introduced you to the concept of fuzzy numbers. So, for a quick recall, a fuzzy number A is a fuzzy set defined over R with the following properties. A is normal, that is, there exists x belonging to R such that mu A x is equal to 1. Second is the support of A, that is 0 plus A, is bounded, and third is alpha cut of A for all alpha belonging to 0 1 is a closed interval. And we have stated a theorem which says that a set A defined over R is a fuzzy number if the membership function mu A x belonging to R satisfies the following. Mu A x is equal to 1 on some closed interval A B, A less than equal to B. It is L x where L is a function from real line to 0 1 and it is 0 in the interval minus infinity to W 1, where W 1 is less than equal to A. And let us continue with that, and mu x is equal to, let me continue from where I ended on the last page, is equal to R x, where R is a function from R to 0 1 such that it is 0 on W 2 to infinity, where W 2 is greater than equal to B. Or pictorially, if we look at it, what I am saying, that mu A x looks like this on an interval say a to b, it is 1. There exists some W 1 such that it is 0 there. There exists a W 2 such that 0 there, or in other words the mu A x will look like this 0 from here to here, it is called L x, from here to a W 2 it is R x, such that beyond W 2 it is 0, before W 1 it is 0, and in the range W 1 to A W 1 to A, L is non decreasing and right continuous, and in the range B to W 2, R is non increasing and left continuous. In the last class, we have shown the necessity part, now I want to prove the sufficiency part. That is, we want to show that if mu A x or the membership function of A satisfies the conditions given above, then A is indeed a fuzzy number. That is, given these properties of the membership function, we want to establish that A will follow the 3 properties of a fuzzy number, and that proof is as follows. First, we want to show that A is normal, this is obvious since mu A x is equal to 1 for x belonging to A b, where A less than equal to b. Therefore, even if b is equal to A, we get the point A such that mu A is equal to 1. Therefore, A is normal. In other cases, when B is actually greater than A, obviously the entire interval A to B will have the membership value 1. We want to show that the support of A, that is 0 plus of A, is bounded. Proof: it is obvious. Since Lx is 0 on minus infinity to the W1 and Rx is 0 on W2 to plus infinity, the support of A, that is 0 plus of A, is contained in the interval W1 to W2. Therefore, 0 plus of A is bounded. Now, we need to prove the property 3, that is all alpha cuts of A, alpha belonging to 0 1, are closed intervals. We prove it in the following way. Consider for any given alpha the alpha cut A. We need to show that it is a closed interval. Corresponding to Lx, let us define a set L such that L is equal to the set of points x such that Lx is greater than equal to alpha and x is less than A. Similarly, corresponding to the set, the function Rx, we define the set R is equal to all those set of x such that Rx is less than equal to alpha and x is greater than B. Let me explain it pictorially. Suppose this is the picture . this is L x and this is R x. So, we consider alpha to be this line. Therefore, the alpha cut of A is this interval, and I am now looking at the set of x which are less than A. That means, I am looking at points in this region, and L of x is greater than or equal to alpha. So, effectively I am looking at this interval for choosing the set L. In a similar way, I am looking at points in this interval for the set R. So, this is going to be my set L and this is going to be my set R. Let x alpha be the infimum of x, x belonging to L, and y alpha be the supremum of x, x belonging to R. So, if we go back to the figure again, then infimum of all these points I am calling it x alpha, and supremum of all these points I am calling it y alpha. Claim alpha cut of A is the closed interval x alpha to y alpha. To show that, we consider an arbitrary point x naught belonging to alpha cut of A. Again, with respect to the figure, this is the alpha cut. So, with respect to this alpha cut, I am choosing an arbitrary point x naught. X naught has three possibilities: either it is less than A, or it is in the closed interval A to B, or it is greater than B. If x naught belongs to A comma B, then certainly x naught belongs to x alpha to y alpha for any alpha. Suppose x naught is less than A, then mu A of x naught is greater than or equal to alpha. We know, because we have chosen x naught from alpha cut. Therefore, x naught belongs to the set L, because x naught is less than A and mu a of x naught is greater than equal to alpha. Therefore, x naught is greater than equal to x alpha, since x alpha is infimum of x belonging to L. Thirdly, suppose x naught is greater than b, then since mu a of x naught is greater than equal to alpha and x naught is greater than b, therefore, x naught belongs to R. Therefore, x naught is less than equal to y alpha, since y alpha is the supremum of x belonging to R. Therefore, for all the three cases, we find x naught belongs to x alpha to y alpha. Since it is true for any arbitrary x naught belonging to alpha cut of A, we can say alpha cut of A is contained in x alpha to y alpha. Now, to show that both x alpha and y alpha belong to alpha cut of A, that will ensure that the two boundary points x alpha and y alpha also belong to the set alpha cut, and therefore, the alpha cut of A is actually the closed interval x alpha to y alpha. So, now we want to show that x alpha and y alpha belonging to alpha cut of A. To show that x alpha belongs to alpha cut of A, we choose a sequence of points x1, x2, xn such that limit n goes to infinity xn is equal to x alpha, and each xi is less than a, and xi belongs to alpha cut of A. If we look at the diagram again, I am choosing a sequence of points xi such that limit of xi is equal to x alpha, xi's are less than A, and they belong to the alpha cut of A. That means, I am restricting myself to this set of points. Since L is right continuous, it implies limit n goes to infinity, L of x n is equal to L at x alpha, because limit of x n is equal to x alpha and L is right continuous. Since each x I belongs to alpha cut, therefore, since L of x I is greater than equal to alpha for all I, implies L at x alpha is also greater than equal to alpha. This implies that x alpha belongs to alpha cut of A. In a similar way, if we choose a sequence of points y1, y2, yn such that limit n goes to infinity yi is equal to y alpha to each yi is greater than b, and thirdly yi belonging to alpha cut of A, that is, with respect to the diagram, I am restricting a sequence of points yi chosen from this interval whose limiting value is y alpha. Then limit n goes to infinity r of yi is equal to r at y alpha, since r is left continuous. Therefore, since r of yi is greater than equal to alpha and r is left continuous, limit I going to infinity r of yi is equal to r of y alpha, which is greater than equal to alpha, implies y alpha belongs to alpha cut of A. Therefore, together we can see that alpha cut of A is equal to the closed interval x alpha y alpha. Since this is true for, since alpha is chosen arbitrarily, all alpha cuts of A are closed intervals. So, we prove that if the membership functions of A satisfies the property as stated earlier, that it is 1 in the interval a to b, it is Lx for all the x less than a, such that Lx is 0 in minus infinity to W 1, and from W 1 to A it is monotonically non decreasing and right continuous, and similarly we get R x for all x greater than b, which is 0 from some W 2 to infinity, and in b to W 2 it is monotonically non increasing and left continuous. Then we find that the corresponding fuzzy set satisfies all the properties of a fuzzy number, and therefore, any fuzzy set over R having the membership function satisfying all these three conditions is also going to give us a fuzzy number. In other words, these two definitions are equivalent. The above theorem helps us in identifying or defining fuzzy numbers of different types. Example 1, let A be a real number. Can we define A as a fuzzy set? Yes. Let B equal to A equal to W 1 equal to W 2. Therefore, what we are getting, if this is A, then in the closed interval B to A to B, which is nothing but the singleton A, the value is 1. In this interval minus infinity to W 1, where W 1 is same as A, L x is 0, and similarly in the interval W 2 to infinity, R x is 0, and thus we get only a singleton point in the support of the set A, which has full membership 1 to the set. Therefore, the real number A can be represented as a fuzzy set. Represented as a fuzzy number. Example 2, can an interval say 5, 10 be a fuzzy number? Answer is yes. Let A is equal to W 1 is equal to 5 and B is equal to W 2 is equal to 10. Therefore, what we have in the interval 5 to 10, we have the membership value 1. Since W 1 is equal to 5, in this interval the membership is 0, which is L x. In this interval up to infinity, R x is equal to 0, and therefore, only the points belonging to the interval 5 to 10 have membership 1, that is all the real numbers between 5 to 10 in the closed interval have full membership to the fuzzy set, and therefore, this is going to be a fuzzy number. Example 3. Let us describe a typical type of fuzzy number called triangular fuzzy number. Typically, they are defined using triplets. A, B, C, such that mu A of B is equal to 1, mu A x is 0 if x less than A or greater than C, and L x is linear in A to B and R x is linear in B to C. So, let me use a diagram. Suppose this is my A, this is my B and this is my C. We are saying that by the above definition, B has the membership value 1. In the interval A to B, L x is going linearly. Before A, it is 0. In the interval B to C, it is going linearly. Beyond C, it is 0, and therefore, once A, B and C are given, we get a unique fuzzy number defined as follows. This is a triangular fuzzy number its membership is going to be as follows: mu A x is equal to 0 if x less than a. In this interval, it is growing linearly. Therefore, membership function is going to be x minus a upon b minus a if x belongs to a comma b. In this interval, for an arbitrary x, the membership can be found as c minus x upon c minus b if x belongs to b to c, and 0 if x is greater than c. So, you notice that when x is a, it is 0, when x is equal to b, it is 1. Here also, when x is equal to b, it is 1, and when x is equal to c, it is 0. Therefore, we can say that W 1 is equal to a, W 2 is equal to c, and this along with the above definition, we get a triangular fuzzy number. Example 4, trapezoidal fuzzy number. A trapezoidal fuzzy number is denoted by 4 real numbers, say a, b, c, d, such that the following holds. Mu a x is equal to 0 if x is less than a or x is greater than d. It is linear in a to b, that is x minus a upon b minus a if x belongs to a comma b, is equal to 1 if x belongs to b comma c, and it is d minus x upon d minus c if x belongs to c comma d. For example, consider the fuzzy number, say around 10 to 12. And suppose the support of the fuzzy number is 8 to 15, such that in 8 comma 10 the mu a x increases linearly in 12, 15 mu a x decreases linearly, and in 10, 12 mu a x is equal to 1. In that case, we shall get a trapezoidal fuzzy number as follows. So, suppose this is 10, this is 12, this is 15 and this is 8. What we are saying, that the membership is 0 when it is less than 8, between 8 to 10 it is growing linearly, between 10 to 12 membership value is 1, and between 12 to 15 the membership value decreases linearly. Therefore, if we look at the shape of the membership function, it looks like a trapezium. Therefore, it is a trapezoidal fuzzy number denoted by TR. Fn also we can write it as the 4th tuple 8, 10, 12 and 15. What is going to be the membership function? Mu a x is equal to 0 if x less than 8 or x greater than 15 is equal to x minus 8 upon 10 minus 8, that is x minus 8 by 2 if x belongs to 8, 10 is equal to 1 if x belongs to 10, 12 and it is 15 minus x upon 15 minus 12, that is 15 minus x upon 3 for x belonging to 12, 15 and 0 if x is greater than 15. You can check that at x is equal to 8 membership is 0, at x is equal to 10 membership is 1, between 10 to 12 it is remaining 1, then again at 12 it is 3 by 3, that is 1, and at 15 it is 15 minus 15 upon 3, which is 0. So, this gives us a trapezoidal fuzzy number. Example 5, piecewise linear consider the following diagram. Suppose in this interval, let me call it again say 10 to 12, the value of membership is 1. At 8 and at 14, the membership is half. as it is right continuous, these will be included there. Between 6 to 8, the membership is 0 to 1/3, and this is piecewise linear, and suppose here between 14 to 15 it is piecewise linear and it goes up to 1/3 to 0. And this is my Lx, and this is my Rx, which are, say for example, Lx is monotonically non-decreasing, here it is monotonically non-increasing, it is right continuous, this is left continuous, and below 6 it is 0, and above 15 it is 0. Therefore, W1 is equal to 6, W2 is equal to 15. In between, this is not a continuous line, but it is piecewise linear. Therefore, this is also a fuzzy number. I like you to work out on these functions, because this equation of this line is coming from that between 6 to 8 it is growing from 0 to 1/3. Between 8 to 10 this line is going from half to 1. Similarly, this is from 1 to half, and this is from 1/3 to 0. Therefore, we can easily find the equations of the 4 line segments, and here the value is 1 anyway. So, that gives us the definition of a piecewise linear fuzzy number. Example 6, it need not be that Lx and Rx have to be linear all the time. A more general scenario can be like this, where these are piecewise continuous and that gives a shape of a general fuzzy number, where Lx and Rx are satisfying the properties given earlier. Therefore, by appropriately defining these small segments of curves, we can always get a fuzzy number. But for this course, because of the ease of handling linear functions, we will restrict ourselves to fuzzy numbers where memberships are given by linear functions, and also mostly we shall concentrate on continuous fuzzy numbers. Okay, students, I stop here for this class. In this class, we have understood what is a fuzzy number, what are the different types of fuzzy numbers and their shapes. In the next class, I shall start with interval arithmetic, and to give you the basic nuances of interval arithmetic, so that when we want to do arithmetic operations of fuzzy numbers, we can take out alpha cuts and then apply the arithmetic operations on those alpha cuts to generate the alpha cut of the final answer. We shall investigate in next few classes how all these arithmetic operations are conducted. Till then, thank you very much.